to me?
Okay, clear, Siti. Can you talk now?
Oh, hi. Can you please answer the polling question that I already flashed just now? You can go to the the more button or the three dot button and then start poll. And can you please answer that for me before we begin this webinar? Thank you. So while you are doing your polling, so I just continue this webinar. So again, welcome to today's webinar, which is overcoming 4 common obstacles to predictive maintenance. So me, I'm Siti Sapwana. I'm from Datastore, which is also distributed from network products, Simulink and MATLAB. So basically, I was covering the area of data analytics, such as deep learning and machine learning, and image processing and revisions. So now, predictive maintenance makes a lot of promises, from reducing machine downtime and eliminating unnecessary maintenance to adding revenue stream for equipment vendors with aftermarket services. So these benefits are imminently achievable as long as you keeping engineering and business challenge from getting in the way. So this webinar discuss the 4 most common obstacles that stop this business from successfully implementing predictive maintenance as identified through more than 1,100 conversations with engineers and engineering managers. So each of these challenge is solvable. This is the webinar will explain how. Again, if you want to interact with me, you can just tap on the chat button there. So we will monitor this question. And if you wish to take the offline topic, you can just indicate that with your email, so later we can entertain you. And this is the pool that I already flashed. And while I'm presenting this topic, you can just answer this pool. And this is the 4 obstacle that I mentioned just now that we will cover on this 1 hour's agenda, which is first, we do not have enough data to create a predictive maintenance. And second, we lack of the failure data needed to for the accurate result. And you understand the failure, but you cannot predict them. Last but not least, you doesn't know how to predict do the predictive maintenance. So basically, this is the first obstacle. So before we begin answering that questions, so let's me briefly talk about what is predictive maintenance. So companies follows different maintenance program to increase operational reliability and reduce cost. So for example, this one way to do this by doing the reactive maintenance. So where the machine is used to its limit and repairs are performed only after the machine failure. So if you're dealing with this simple operation, then it might make sense to go with this reactive maintenance. But think of the complex system with some expensive part where you can really risk the running of it to be failure. So as it will be extremely cost to repair highly damaged part. But more importantly, it's a safety issue. That's why many organizations try to prevent failure before it's occurred by performing regular checks on their equipment. So one big challenge with a predictive maintenance is determining when to do the deep maintenance. So since you doesn't know when the failure will occur, you have to be conservative in your planning, especially if you're operating safety critical equipment, but by scheduling maintenance very early, you are wasting machine life, which is still usable, and this also adds to your cost. However, if you can predict when a machine failure will occur, you can schedule maintenance right before it. So the good news is that you can do the predictive maintenance, so lets you estimate the time to failure. So it also pinpoint problem in your complex machinery that help you to identify what part you need to be fixed. So this way, you can minimize downtime and maximize equipment lifetime. There's a few of examples from the companies has already implemented the predictive maintenance in their organization or their work. For example, these are Siemens use predictive maintenance to their electronic trains, where it's achieved 99.9% availability. So others like ABB, Intel, John Deere, and Bosch take benefit of predictive maintenance as well. So not only in certain industry that cover of the predictive maintenance, but we can see every industry or any manufacturing that have the operating machinery basically, we are able to do the predictive maintenance such as aerospace defense or automotive if you in the medical devices, as long as you have the data, you're able to do any predictive maintenance. So this is the area of the predictive maintenance cover. Now we go to the agenda that we do not have enough data to create a predictive maintenance system. So this obstacle is like you can see many predictive maintenance approaches rely on the machine learning algorithm. So there must be enough data to create an accurate model. For predictive maintenance, data usually originates from the sensor of the machinery. So if the sensor are new or the way of reading a log limit the information, you will need to think about the way, the best way to access the data to build your model. So for the first approach you can do is you can take a look at your data or your list of your data source. So you might find that your department doesn't have or doesn't enough collect that data to power the predictive maintenance system. So you can consider whether other departments collect the data as well. So perhaps if you are in the control division, does not collect enough data, but what if other combine with the data from the services division? So you can looking further within your organization could be enough to meet your needs. So depending on your size of the business, and where in you're in the supply chains, it is worth looking your agreement with your supplier or customer. So by cooperating to prolong and health and sufficient of the equipment component, you may put your win-win situation that foster data access between business entities. So but sometimes this will not always be the case, but it is potential data source that merit considerations. Next is you might change how the data is captured. For some system, you operate in the piece or framing mode where it's little to no data is collected until the fault occur. So others only log event code and timestamp. So engineers are notified that the event occur, but not the sensor value at the time of the failure. So although this data is maybe useful for diagnostic, but unlikely it insufficient for developing model that can predict the failure. So considering changing the data logging options to record more data, perhaps on the test bed in the production data is not available, depending on the load on existing embedded devices, it may be possible to reconfigure them to collect and transmit sensor data. Or you can have the external data logger may be necessary to get started. Last is like you can use simulation tool to do the data synthesize. For example, you can generate data using the simulation tool such as our product MATLAB and Simulink, and you can combine that data with the sensor data is available to build and validate predictive maintenance algorithm. So this is done by creating models in the Simulink that covers the mechanical, electrical, or other physical system to be monitored. So this synthesize that data by modeling the output reading and the validation against the measurement data to ensure this model will calibrate, and this can be done in the component level first, then later in the system level for the complex system. This is one of the user case from Mazda where they use a MATLAB and Simulink to synthesize the data. So Mazda needed to define test plan, develop statistical model, and generate optimal calibration for their sky activity engine. So they developed statistical model for the sky activity and perform hardware in the loop HIL simulation of the engine control logic. So as a conclusion for the first limitation or first obstacle, so when considering the data for the predictive maintenance system, begin to analyze data early to understand which features are important and which are maybe redundant. So depending on where your data store, it can be expensive to keep an excessive amount of data is not going to be used. So when you understand the feature of the data, that what is important, then you can make informed decision which or about data need to be kept or not. So one of the tool like a MATLAB is they can decouple from the storage system if you move from the cloud or local to cloud, so you can still running your analysis with minimal changes. Now for this second obstacle is you lack of the failure data needed for the accurate result. So this failure data actually is a crucial part of a teaching algorithm to recognize the warning signs to trigger just-in-time. So failures data may not exist in the maintenance if performed so often that no failure have occurred. So of the system is safety critical and it cannot be left to fail. To stop this from becoming a better dependency, you and your team can simulate the data and then how to recognize warning sign from the available operating data. So an engineer with a sufficient domain knowledge can incorporate this behavior into the model in the varieties of scenarios which can simulate failure data by adjusting temperatures, flow rate, or vibration, or adding other sudden spot. So this scenario can be simulated and then we can result failure data and label, store them for further analysis. So you can use Simulink to do that. For example, this Airbus, this Airbus needed to safety handle failure in the compact full management of their system for A318 model Airbus here. So the team simulate failure data to refine the model. So after successful flight test, they evaluated the differences differences between the measured data and the predicted result to further tune the model. You can use Simulink, generate the fault data, and then a part of that you need to understand the data, your available data. For example, failure data might not be present, but the operation data might show trend about how a how a machine degrade over time. So looking at the raw sensor from the component system or machine, or even the dozens of the sensor can be intimidating. statistical technique such as a PCA, principal component analysis, can help reduce the dimensionality of such a data set and provide valuable insight into how equipment operate over time. So it can be it's depending on your sensor, what sensor available, and certain type of failure may be required looking at the several sensors simultaneously to identify undesirable behavior. So unsupervised technique transform the raw sensor data into the lower dimensional representation, which can visualize and then analyze much more easy than high dimensional raw data. Next, once you already have the data, you understand the failures, but then you cannot do the prediction. So, understanding the cause of the failure is important for your business, but there is the significant difference between identifying what went wrong and knowing how to predict it. So, root cause of the analysis is an integral part of the domain knowledge that are paired with the predictive maintenance algorithm. So, create an effective predictive maintenance program. If the algorithm part is of the equation is new and intimidating undertaking, you can take this step to reduce the learning curve. So first, you need to define the goal, right? To understand the failure data. You want to predict do the predictive maintenance. So how do you know this predictive maintenance algorithm is better than previous way of doing this? It is important to define your upfront what's the challenge of your goal. For example, early identification of failure, or you want to estimate longer cycle, or you want to decrease the downtime. So you should know then how to predictive maintenance algorithm will affect this goal. Is performance, building the framework that can test this algorithm and estimate its performance relative to your goal will enable faster design iterations. Then you can strive to start small. If you and your team already know the causes behind the failure, then domain knowledge is there. Choose a project using the deeply understood system to practice on. So make sure you understand the features and the factors to affect the performance of the system and build the predictive maintenance algorithm. As the simplest as a starting point, it is worthwhile to consider its threshold of feature is a significant maintenance indicator. So beyond that, you may try simple models such as a linear or logistic regression, which are quick to pick and easy to interpret. So when you and your team are comfortable with the building the algorithm for simple problem, then you can apply the knowledge to more complex system. Lastly, you need to gain the confidence. When the predictive maintenance algorithm begin to show a promising result, then you use the current and historical data to test and validate the model before you move to the production. When you want to upscale that. Use the domain knowledge again within your team and tune model to predict different outcomes based on the cost or severity of those outcomes. To further validate model, then you can add more generate, or maybe you can generate more failure data similar to the non-historical condition and test the system. So this validation step will build confidence that need the process, or either whether it's working or not. There's can be done with this endorsing the model's accuracy. And then the last, obstacle is we do not know how to do the predictive maintenance. So I will walk you through a workflow that help you to develop a predictive maintenance algorithm using our product, which is MATLAB and Simulink. You will learn how to about condition indicators and how you can extract them from your data to discriminate between healthy and faulty state, And you're also able to learn machine learning models that train using the extracted condition indicators to classify different type of fault. I will also help you to understand different estimator models that are used to estimate the remaining useful life of a machine. So basically, this is the overall of a framework to perform the predictive maintenance, workflow. First, you can see this green arrow first, which is first you need to design, deploy, and then you upscale into your in operation or production. So in design part, you might see your access and explore data. It comes with the various part, which is it comes from your sensors, my asset itself, or maybe from the enterprise system or OT IT system, or in the edge system. You can just input your data, access it through the design part, and then once you already have the data, you need to do the processing, which is that multiple sensors combined together not will result a good accuracy or a good data collections. Must be some noisy or outlier and etc. So you need to do the processing data first, then you can do the identify condition indicator, which is can be a features that is useful to distinguishing the normal from faulty operation or to do the predicting remaining useful lives. So you can choose in this step is either you can do time domain or frequency domain or time frequency domain features and etc. Then you have the features. Now you can do the train model by using the machine learning technique or others AI techniques. If you already finish on design part, then you want to integrate or deploy it to your smart asset or in your operation system. Whereas you need to deploy your predicted maintenance algorithm, and in this whole process, from the designing to the deployment, you can done into one in this one platform, which is MATLAB Simulink. So that's overall of the frameworks. Now we go to the more deeper on the framework just now, but this one is from on the workflow. Again, I will cover the access data, where's the data you come from, even the from the sensor data itself, or maybe you doesn't have let's say much faulty data. You can do the fault generate data synthesize with the MATLAB or Simulink tool, and then you do the pre-processing. Next step is identifies the condition indicator and the train model, and then do the deployment and integration. Let's goes to the accessing data first. If you recall just now, I mentioned that you can access data by the sensors, the OT system or enterprise system. This is we call this a digital twin technique, where you can access the data through the digital twin. So what is the digital twin? This is an up-to-date representation or a model of an actual physical asset in the operations. So it can be model of the components, a system component, or the system such as a pump, engine, power plant, manufacturing lines, and etc. So digital twin models can include the physical-based approach. You can see first principle modeling, or statistical approach, or more on the data-driven modeling. So the model reflect the operating assets current environment, age, and the configuration, which typically involve direct streaming of an asset data into training algorithm. So modeling method generally can be grouped into two types: first principle, or or we can say like a physical based method, example mechanical modeling or model of the system or component or any electrical mechanical algorithm and etc. And then the data driven, like I mentioned just now, is inside the deep learning technique or machine learning technique, where you synthesize or you create the from the data. And digital twin also can also be composite of a various model behavior and can model methods, and is likely to be elaborate on over time. as more use as are identified. So once you already, we also have a function, we call it as a data store, where is you can just, you know, this data store function is is point your data in the any file or any directed data that you store is either in cloud or in local disk or in database. So basically, it just point the directory. Instead, the software load all their data into this MATLAB. So you can imagine that they just point into that point is either in cloud or the local disk, and it make this computational resources is more available to do the next step instead of the taking all those hardware resources to perform the accessing data. So in MATLAB, we do have this function we call data store for your data, such as a Excel file, TXT file, or CSV file, any file, but not limited to that particular data type. We also have image data store, where is in the image form, and others like a spreadsheet data store and tabular text data store. And for you if your data type is in the audio, we also do have the audio data store. The concept is same, it just point into the directory instead loaded all your data into the MATLAB. For example, this Saffron, they use Simulink to generate data instead of the point to the data because they doesn't have the enough data. So they use another technique to access data is generate the value data. So Saffron also do this for to estimate the remaining useful life and they want to detect anomaly. So that's a three type of data accessing. Now we go to the second part, which is pre-processed data. Like I mentioned, data in the real world is rarely perfect and it has an outlier, noise, and that need to be removed to get a realistic picture of a normal behavior. If the data has come from a different sources, it will have also need to be combined. Then the data for pre-processing data is must have like sometimes they have like missing data or layer or noisy. So here the part or the step where you want to smooth your data or maybe you want to do the normalization on your data, so that we call the processing data. That's already mentioned just now. Data, if you come from the different data source or sensor, you come with the poorly formatted file, irregular sample data, and redundant data, outliers, missing data, and etc. So depend on your data itself for MATLAB. Or you want to do the pre-processing for the signal. Mostly, the easiest or the popular technique to do the pre-processing is just like smoothing, resampling, denoise, and rapid transform for the pre-processed data for the signal. While for the images, if you do have the different source or different images, you might have want to register your image by using the image registration. And also you need to enhance your image, like you can perform morphological filtering or deblurring and etc. While for the audio, I didn't include in the slide, but how you want to do the pre-processing data, you might want to extract like your MFCC, your mass spectrum or linear spectrum, even the pitch. That is how you can do the clean up of your data. But the most important thing is for this pre-processing data is you need to be creative. So let's say, for example, you have a signal data. So in MATLAB, we do have apps. We call this as live editor apps, where these apps, live editor, is they have tasks that can be added into your live script to perform the specific set of operations of a pre-processed data. So you can add tasks to live script to explore the parameter and automatically generate code and use this task to reduce development time. and development times and errors, and time spent for plotting. So tasks represent a series of a MATLAB command. You can display their output in the inline or the right, or you can see this MATLAB command that the task run and show the generated code. For example, here I just run the smooth data in the particular uh, live editing task, and you can toggle either you want to put it in, or just show the code, or you want to hide and automatically display the output there. And then you want to change others preprocessing task. For example, this one is define local extrema, and you can just manipulate the parameter there, and it will show the output automatically on the spot. So this is how you can do preprocessing in this live editor. If you can see the right hand side, there's a lot of functionality. It's not just a smoothing. You can see you can do a file missing, that can field missing, and etc. To depend on what your application you want to use or what process you want to use. Next, you want to identify the condition indicator. So instead of you feeding your sensor data directly into your machine learning model, it is common to extract the features from the sensor data. So these features capture high-level informations in the sensor data, for example, moving average or frequency contents. The field engineer have a strong background in the statistic, signal processing, and system modeling. So the use of this familiar tool to perform features extraction techniques simplifies this step. The an iterative approach in which features are added. The new models are trained and their performance is compared. So this can work well here to determine the effectiveness of a different feature on the result. So the challenge here, the main thing you want to do the condition indicator is very useful to you to distinguish between the normal or operation uh, system, or you want to predict the remaining useful life. But the challenge here is you need an expert domain to know the features extraction and how to do the identify keys condition indicator. This is signal-based condition indicator, whereas you can see if you know that signal-based, you can extract those features from the time domain features, frequency domain features, or time domain frequency features. So this is more or less what the features you can extract. So in MATLAB, we do have one app we call Diagnostic Feature Designer app, which is in this toolbox, predictive maintenance toolbox, which just introduced last year, 2019, in R2098. So we can use this apps to extract time domain and spectral feature from your data to design predictive maintenance algorithm. So in this example, if you want to measure, the measurement has been collected from the pump, triple pump, under different fault condition. So the apps lets you to import this data interactively and visualize it. So this is the pump data. As you can see, I just import it. The pump data is come with the flow and pressure for the pump. All right. So once you already okay. So now you import the pump data. So let's import it to you and just so once you import the pump and pressure data, you can visualize it inside the apps. For example, you can just trace this signal by using this trace signal tab, and you can just view it by group of fault code. Okay, that like as mentioned just now, this is a pump, a triple pump, where you want to extract this picture, and this is the code where you want to classify is either you have a fault code of number 111, 110, and etc. So once you already visualize this pressure of flow data, now we can go to the time domain features. We can extract it for the flow data, and you can see this the statistical or basic statistic like mean, standard deviation, or in a high order statistic, we do have the kurtosis and etc. Let's the X just extract down to you. And then if you want to continue extract for the spectral features, this app can use like time domain data just now to estimate the signal spectra of this signal, which is can be then used to extract spectral features. That's so we select the spectral and click the power spectrum. Here you can try out like non-parametric or parametric method to compute the spectrum and compare the result. So we can choose auto regression models with models or orders or and etc. So next we need to compute the spectral features. So we just we click here, and then we can select the frequency band that's included for the first peak. Let's see the peak where you can just select. And then the reason is that due to the noisy data at the higher frequency, it is harder to distinguish the spectral peak. So therefore, any features extracted from the higher frequency won't contribute the performance machine models or machine learning model. Then once you already got for the flow data, you can repeat it for the pressure data. That is the features extracted for the both signal in the time frequency and spectral frequency. You can visualize it in the form of table. Now the question is which one is more sensitive to your machine learning model. So because there's more than like 20, even it depends on your signal, but in this case is more than 20. So how you rank them? So we can go to, this is just a visualization where just a histogram based graph. So we want to know which signal is more relevant or more sensitive to your data. You can go to rank features button here, where is we rank what is you can features that you can use to train your model after this. And the way of they do is one way ANOVA ranking. So you can see it will rank all from the the highest value to lowest value. So you can choose either all, or you can take like top 10 or top 20. It depend on your applications to perform which to select which one is more relevant to you. Now you can just export the relevance pictures to your workspace, or you can just export it to your classification learner apps, which is one of the apps in the machine learning statistic and machine learning toolbox in the MATLAB to do the training part. So basically, that is for the identify condition indicator. Now we go to the train part. Also, in this step, you can classify data as a healthy or faulty, or you can set the threshold for the healthy, warning, or failure state, and estimate remaining useful life for the components. So you need to create a comprehensive list of the failure scenario to predict or choose classification method and simulation method. So there's an app provide a graphical interface for applying the machine learning that make it easy to get started and compare results for the training many different types of model. So this is basically the AI, and you can see the subset of the AI is a machine learning, and the subset of machine learning is a deep learning. So AI is a simulation of an intelligent human behavior. It is a computer or system designed to perceive its environments, understand its variable, and take action. So consider like self-driving cars or AI driven system is like this integration algorithms such as machine learning and deep learning into the complex environment and enable the automations. So depend back with your data. So which direction of your AI you want to choose is based on these two parameters on the data or the time. If you have less time and less data, so you might consider to do the wavelet scattering first to do the feature extraction, which is one way how you can do the feature extraction other than the designer app just now. And then once you already have a sufficient enough feature or data, then you can go to your upper level, which is deep learning or machine learning. Because sorry, deep learning or transfer learning, because you know machine learning need a volume or high volume of data to perform the training. And then if you do have maximum or more data on more time and less data, you can try to artificial or generate the data first to get the high volume of data to feed it into your AI. So basically, this is how you can perform your AI based on your data availability. Then let's say you have already create things with your data, and you know you want to use the machine learning technique to perform your PDM or predictive maintenance. So machine learning, as we know, we do have like two types of machine learning, which is supervised and unsupervised learning. Supervised is where you do have a both input and output level, such as in the example or any input, like you have the signal and you know the signal is belong in which category, and you know the output. So that is the supervised learning. Or unsupervised is you doesn't know your input data, but you're using some clustering technique to do the group or make it become the supervised learning. So that's different between supervised and unsupervised. So for the supervised learning, we do have two types of the categories of algorithm. First, regression, and second, the classification. Regression is for time series data where you want numeric data, so where you want to predict like fluctuated of the electricity, or you want to predict the stock market, you know, the time series data. That is the regression. For the classification is you want to perform the discrete type of data. For example, you want to know this machine is failure or not, or you want to classify the picture of your object, and that is the classification. So when in the machine learning workflow, this is the basic, the standard workflow for the machine learning. First, you need to train your model. So by training your model, of course, you need the data, and this is the historical data you feed it into your model. And of course, you need to do the pre-processing data. Once you already do pre-processing data, you choose either supervised or unsupervised. If you do have know that there is a supervised learning, then you can choose either you want to do the classification or regression. Once you already have the models, then you want to predict, you need to have your new data and then apply that trained model and then do the prediction. So that is the workflow of machine learning. Well, let's say this is for the classification case of machine learning. We do have this example like fault diagnosis, still using the same example, the pump just now. So what I can do is, if you recall that this is the feature diagnostic, diagnostic feature designer apps that I've done in this example is I just select few feature that I think is important to my training data, which is sensitive, then what I can do is I just export these pictures to my machine learning app, which is classification learner apps that uh, will train my model. You can directly import from that apps, one apps to another apps to just make it continuous step. So in this apps, you can see because I want to predict the fault. So the response here must be a fault code, which is what the classification of the fault, and then the predictor is the features that might important to my train data or predictions. So if you can see, this app will help you or allow you to train all the machine learning model simultaneously at the same time. And then one is already trained, it will give you the best, it will highlight to you the best result for you to, make it the further process. For example, this one is medium tree algorithm have most accuracy. So you can try, if you can see this is not much accuracy, then you can go back to the feature selection and deselect which feature you might think unnecessary. For example, this one dimension. You can deselect and then train it back, and you can play around with this app to see which accuracy is good. Then if you satisfy, you can just export the model as uh, a function, or you can just export it by using this generated function where it can generate the MATLAB code for you, so it doesn't need to do the handwritten coding. That is the apart using classification learner apps. And then the second thing you want to do for the predictive maintenance is you want to predict the remaining useful life estimation. So this is RUL, is a length of a time of a machine likely to operate before it's required to repair or replace. So by taking this RUL, remaining useful life, into account, so engineer can schedule maintenance, optimize operation efficiency, and avoid unplanned downtime. For this reason, estimate RUL is a top priority in the predictive maintenance toolbox. So this is the RUL model estimator, whereas again, it depends on your data. If you can see that simulating model, it comes with the range of the healthy data and the failure data. While for the survival model, it comes with a failure data, was it much many, failure data is more than the healthy data. But for the regression model, you have a healthy data up to certain level of a failure because you already set the threshold, safety threshold for that. So again, when you want to do this RUL estimator, you need to know which range of your data have. So this is the method of RUL method you want to use once you know the uh, data. For example, you have like simulated model. In this, we MATLAB also have a huge amount of function to predict the RUL. It's either in the hash simulated model, pairwise simulated, or linear regression, exponential regression, and for the survival, we do have like reliability survival, covariate survival mode. So this is all on the form of the function. You can just pull the function and do the process. For example, this is again for the pump data, but this is for the regression model where it's already set the threshold -9, where that is the safety threshold that I mentioned just now. So what is you can do is you can have the data, the features extracted as well, and then just plug in the exponential regression model that is offered in this predictive maintenance toolbox. You might see the documentation, what is the others remaining useful life prediction model like I mentioned, this like regression model, similarity models, value model. You can just plug any model depending on the data. Then put it into your MATLAB and put any the process, and then you can estimate the remaining useful life. Just fast forward and then you can use the predicts RUL function using this your model just now. Then this is the model, then you can do the predict remaining useful life by using this predict function come together. So this is the model that the pump model just now, but in this certain range. But once you plug that particular function, it will give you one nice form of plotting where you can estimate this pump remaining useful life. For example, this one is estimated before the safety threshold is around 4.6 hours. So this is how we can do the remaining useful life in the MATLAB Simulink. Last but not least, you want to deploy or do the integration of your model to the embedded devices, or by converting them to the low-level language such as C or GPU or HDL. Or you may want to integrate with the other application in the IT environment or enterprise level. The pain here is often around lack of familiarity with the code generation and IT integration. So for the deployment part, we do have products to you to perform the overcome the limitation. For example, if you want to deploy to your hardware, we do have several recorder product that you can convert your MATLAB code into the specific embedded hardware, such as your ARM processor or even your FPGA. Even for your GPU processor, we can do have a several product to perform that. And then for the enterprise level, we do have a MATLAB compiler to you to create your own standalone application in the MATLAB. We call it MATLAB App Designer. Then if you don't have a third-party apps, you can just use a MATLAB Compiler SDK to do the integration of your train model in the MATLAB to that particular software. So now we talk more on the what is MATLAB Compiler and Compiler SDK. For example, this MATLAB compiler I mentioned, you can use this to enable you to share MATLAB program as a standalone application and web apps. This is the app designer where you can create the apps in the MATLAB. So you can also package and deploy MATLAB programs such as a MapReduce or Stock big data application as Microsoft Excel add-in. So any user can run your application royalty free by using the MATLAB runtime. So you can create this standalone application with the MATLAB program and share them with the other non-MATLAB users. So you can see, let's fast forward. This is just apps that are created in this app designer, and you can take this share button. Share button here, you can see the option of MATLAB apps, web apps, and standalone desktop apps. So this is for the desktop application. Then I'll just select the desktop apps and let's do some documentation for the apps, and then just package that until it is regenerated ASE file to you to share to others user to install to their computer or laptop or other things. So that is the standalone application. Then we also have web apps. Instead of running in your local PC, we can run that in your apps. In the web. So each package MATLAB program itself as a web apps and share using this unique URL. So you can see instead I choosing the standalone application, I choose the web apps and do the packaging. Once I already have the CTF file, I just paste it into my search folder and it will automatically detect the apps. And then you can share this URL to others users to them to access your apps. So that is on the web apps. And this is MATLAB Compiler SDK. It's an extended of the functionality of MATLAB Compiler. Let you build your C or C++ shared libraries or Microsoft.NET Assembly, Java, classes, Python packages from the MATLAB program. So let's take some. We do have MATLAB production server that will host your MATLAB program in the secure, scalable, or manageable platform with the MATLAB production server, where you can integrate with third-party dashboard such as Spotfire, Tableau, or Power BI, and then still the backend still use the train model using the MATLAB, but your front end or your visualization just this tool. This is how you can do MATLAB compiler SDK in the MATLAB. You can just choose appropriate for apps, which is MATLAB compiler server, and then just put it all the necessary function. And because this is this app also let you enable you to test the server and the client. So you can just put the server or port name and let them communicate and see is have any error or not. Then it's already completed the test. You can package that. Once it's already packaged, you get also the CTF file and give this file to your IT department to do the integrations. That's all. And once you already do the integration, you can see this is the load forecasting. Doing the regression machine learning model, use the regression learner apps from the MATLAB, and we plug with the AWS environment or dashboard to do the visualization. So this is a compiler's compiler SDK. So this is overall of the products. And then now you want to see the embedded hardware where you can deploy or you can, convert the MATLAB code into this particular code. For example, this is our CPU, GPU, and FPGA that I already mentioned just now. Matter of that, we do have a apps we call that a MATLAB coder and MATLAB GPU coder. This is one is for you to translate your MATLAB to the C and C or C++. One is one you want to translate to the C on the coder base. So the apps is same because this is different apps, but they're using the same concept. Which first you need to import your function, and then you need to do the input type of what your input type. Then it's either you can do automatically or you can just create a test bench to let the apps automatically detect the input type, decided on it image how what is the width or what is the height and what is the color channel and etc. So once you already have this suitable test bench or type, then you can choose either you want to put it into your Max or C++. It will directly translate to you, and you can visualize the generated code within this app and see what is you can even adjust the code over here, but that's not necessary to do that because it's already once it's already converted, it's able to use or integrate with the others. However, for the GPU, is also come with the memory allocation for you to doesn't need to handle that such of configurations. So this is the predictive maintenance user story using our products from Bosch, Bakery Rogers, Safran, Mondi, and etc. You can then you can see this in the MATLAB documentation or MATLAB user stories. And the summaries of today's presentation is you can do and explore the automated feature extraction and machine learning tasks by the apps given, and you can deploy or convert your MATLAB code into your targeted hardware, not just at C or C++. We also have a GPU or HDL. You can also integrate on the enterprise level. And if it doesn't have enough data for the failure data, you can generate it with the MATLAB Simulink or Simscape by do the physical modeling and you know inject the generated failure data and get the synthetic data. And you can do the try to start doing this by using our reference model or reference example from the documentation page. So this is the predictive maintenance with MATLAB. We will if you can if you want to perform the predictive maintenance, this is a example of a you know series or white paper you can download to explore, and this is the code example you want to try on later. So before I ending up this webinar, I would like to you to do one more poll. Okay. This is just like 2 minutes of your time. Okay. Okay. Can you please answer this while doing the when people be ending up this presentation? And once you finish the pool, you can scan this QR code to you to evaluate this our presentation, so we can continue to improve our future webinars. I will I'll leave it around 30 seconds to do that. All right, so a part of this is an upcoming lab event, so you can go to this website to know what is upcoming events. Is we not just cover in the predictive maintenance, we also on the data science area or image processing area, or even the robotic and simscape and physical modeling or any others hot topic. So you can just go to this website to see what is upcoming webinar or MATLAB event. Part of that, we also offer consultancy and training services, whereas you can just contact us for this type of support. And if you already a MATLAB user or similar user, you can just reach us on the support at datastore.com to get our 24-hour support. And then you can also, if you have other inquiry, you can just email at event at datastore.asian access event at datastore-asia.com to request of any other inquiry you want, or you can contact us by the given telephone number there. I guess this is maybe it's taking 40 minutes of your time, but you can just email us if you have any questions regarding this webinar or any others query as the stated email that I mentioned just now. So this is the last slide for my presentation today. Thank you for your time for this 1 hour 5 minutes presentation or webinar. Thank you so much for attending this.